I think it's, yeah, and
Is
if
it
I have
okay?
this little thing, the recording button, I assume it's
Okay. So do I need to talk to the microphone? I guess I should.
I think it is.
All right. Hi, welcome. I'm Reza Shadmer, and this is Scott Albert's thesis defense. Thank you for coming. I just want to take a moment to tell you a little bit about Scott. Many things you know about him already, but a little bit that I've learned about him over the years. I'll start with his awards, and I want to tell you that basically there is no significant award that I know of that he hasn't won while he's been at Johns Hopkins. So he came to Hopkins in 2013, having been awarded the George Pepper Award at Lafayette, where he was the highest honor that they afford to an undergraduate. So I often think that when Johns Hopkins takes the best student from any university, you can expect good things from that person, and Scott has certainly lived up to that expectation. In 2015, he was awarded what's called the NRSA, which is a award that's given by the National Institutes of Health to support the doctoral work by the student. In 2016, he won the Best Project Award at the Computational Motor Control Summer School. 2017, he won the Best TA Award. 2019, he was awarded the SIBO Award, which is given to 5 students that study bioengineering at Johns Hopkins, MIT, Berkeley, UC San Diego, and one other university that I can't remember. A good place, let's say. Finally, a few months ago, last month, he was awarded the Matt Strand Award. He is the 4th student in our history to have won this award from our lab, and it's given to outstanding research by a young investigator at the School of Medicine. So he's done well. His research has done quite well. So welcome, guys.
Hello. It's quite a church.
I want to end with just a personal note about him, to give you a sense of the kind of person he is. Many years ago, I would take my students out on, I think, Fridays, and we would go out to pick up garbage around the neighborhood. You know, most people, when they pick up garbage, what do? We have a bag, and you walk around and you pick up the cups and the cans and the pieces of paper and things like that. But that's not the way Scott picked up garbage. Here's what he does. Scott picks up a piece of land that he focuses on, and he picks the minute pieces of garbage that are on the floor, the cigarette butts and the little pieces of paper, and he completely cleans that little piece of land. And I think that gives you an indication of his character. It's about detail and you know, making sure that the work is beautifully done in that small space in which he has focused on. And I think that reflects in the research that he does, which is what makes him a great scientist. Smile.
Well, thank you, Reza, for the introduction, and for all you for coming and braving the storm, so to speak. Let me just make sure this is functional, actually. Why did that not work? Okay, perfect. All right, thank you all for coming. I want to start with just a really quick video of someone doing something that is really simple. So you're going to see an individual here that's going to pick up a cylinder with his right hand and place it on a peg in front of him. Oh, and you're not going to hear the volume. There you go. So, not too impressive. Oh, all right, already having catastrophic difficulty. Hold on. All right. I think the Zoom call is kind of screwing up something. That shouldn't be happening. I don't know why it's happening. All right, guys, last try here. What I want to do is pause it there. Okay, So you saw him do it about 5 times now. He's very good at this with his right hand. And this isn't surprising. We do things like this all the time, right? We manipulate objects, we move our arms, we maintain stillness without any thought as to how our brains are doing this. And so we don't know how the brain really does this, but we have some ideas of the areas that are nevertheless important for such a task. And so there is this part of the cortex of your brain, which is the surface of the brain, your motor cortices, that have neurons that really like these types of things. They are what is necessary to perform these tasks accurately. And they send signals, electrical signals, down a pathway called this cortical spinal tract, cortex to spinal cord. That is what is used to basically control your arm while you're doing such a thing. And this pathway ends down in your muscles, and that causes your muscle to contract and therefore produce a movement like you see. And so for all of us that have an intact cortical spinal tract, we do these things all the time, and it's not difficult, right? But when you have damage to this pathway, so if you've had a stroke that has damaged the cortical spinal tract in some way, this task is no longer simple. And so now this is actually a stroke patient that with their other arm, which is the side that is affected by the stroke, they're going to try to perform the same task after a quick blackout. And what you can appreciate is that this individual has very severe difficulty picking up the cylinder and then eventually moving it over to the peg. I'm not going to show you the whole video, but you can appreciate that they have a pretty severe deficit in their ability to control their arm because this pathway has been damaged. So in lab, we're interested in studying movements and understanding how they're performed and what affects their quality and how to make them better. And the way we measure these is we get models to come in and hold on, not models, but we get people to come in and hold on to a robotic handle while they're making movements and on a screen, and they might see something that looks a little bit like this, where they have a display. They start off at a certain position and they make a reaching movement to a target, and their trajectory might look something like this. And so in that patient that I just showed you, in their good arm, the side that's less affected by the stroke, this might be an example of several trajectories they might make as they're reaching from the starting position to the target. But after the stroke, on the affected side, that quality of the movement is significantly deteriorated with more erratic and elongated trajectories and an inability to basically move accurately. And so what it's safe to say is that when you have damage to that cortex, that cortical spinal tract that I mentioned to you on the previous slide, it impairs your ability to control your movement. But it doesn't necessarily obliterate the ability to move, obviously, and to also learn how to move better. And so what we also study in lab is not this process just of control, but how do we learn to change our patterns of control? How do we learn to move better when we experience errors? And so a really common task that we do is people move between a starting position and target, and we apply a force field, something they've not experienced before, that perturbs the motion of their arm. And because the brain doesn't expect this to occur, what happens is their straight line movement becomes this really elongated trajectory. And it's an error that they experience that they didn't expect. And what happens is if you do this many, many times, the brain has this wonderful property that it's able to learn from these errors and it's able to compensate for the types of perturbations it experiences. And so a compensation for forces that push you down might look something like this, where the brain learns to produce forces in the opposite direction over time. All right, so this is in the good arm of that stroke patient, or actually the population of stroke patients that is included in this particular study. And what I'm showing you here is what I'm going to call a learning curve, and this is really important for the rest of the talk. What this is on every reaching movement what we're tracking is how adapted is this individual to the perturbation. And so 0 would be they're not adapted, 100 they would be perfectly adapted. And what you can see is that learning is a gradual process. They keep experiencing these errors over and over and over and over again, and they gradually learn to increase the forces that they need to produce to compensate for those errors and then move straight. Now, I'm going to overlay on this the bad arm of the stroke patient. This is the arm that's affected by the stroke. And so these are the forces the bad arm produces on average, and then this is the learning curve over time. And what you can see is there's really little to no deficit in the ability of these patients to learn. So adaptation is more or less normal, at least in the context of this experiment. And so what's strange is that you damage this pathway that's really important for movement in the primate. Motor control is affected, but this process of learning is relatively normal, or at least less affected than movement. And you can kind of imagine that as you're able to like learn a new word, but you have trouble pronouncing the word. That's kind of like what this deficit would be like in more cognitive domain. And the reason why learning is normal, we believe, is that this damage to the brain didn't affect another area of the brain that's also really important for movement, and that's the cerebellum. And it's a lot larger than you can see here, but I've outlined the region that's visible. And the cerebellum is half the neurons in your brain, and we think it's very critical for learning in the motor domain and actually probably in the cognitive domains too, though that is not as much as known about that. And so what we're going to talk about today is this idea that the brain has multiple areas that care about a movement. The motor cortex is what is involved in producing an accurate movement. The cerebellum, we think, is also involved in learning from error and keeping your movements accurate and learning to respond to different perturbations. And what we're going to do today is I'm going to start with this process of what we believe to be a cerebellar adaptation. And we're going to unpack a little bit about the properties of how the cerebellum adapts to error. And then we're going to transition into linking that into how we think the cortex is controlling your movements and also how you don't move, how you hold still. And we're going to do that by addressing 3 separate questions that I'm going to just briefly highlight right now. So the first question I'm going to talk about is, how does the brain learn from the occurrence of a single error? So you have that one perturbation. What happens on the next trial? And so when you have a force field perturbation, you already have seen this would be learning after a single trial. So after you experience a single error, these are the forces that a subject produces. And the question is, why do they choose to produce this force? Why not produce a pattern that looks like this or a pattern that looks like that? So what are the properties that determine what your arm is doing as a function of time when you experience an error? That's the first question. The second question, we're going to talk about how this changes over time. And so another remarkable property of the brain is that the way you respond to error doesn't just stay the same over time. It changes with your experience. And so we're not going to talk about stimulation today, but just to motivate this idea, if you actually stimulate the cerebellum, you can actually change the amount people learn from a single error. And so if you just sort of put a battery over the cerebellum, this is a direct current stimulation, you can get people to learn more from a perturbation. Or if you stimulate with the opposite polarity, you can actually get them to learn less from a perturbation. And so this just, again, highlights the importance of the cerebellum in this task. But again, I'm not going to talk about the stimulation today, but I'm going to talk about this idea of changing the amount that you learn from an error. Last but not least, another thing you can appreciate from learning from a single error is that not only do people change the way that they move, and this is a movement perturbation, and so when they get to the target, the robot's no longer producing any forces on the hand. But people don't just change the way they move. They also change the way that they hold still at the end of the movement. And this is a puzzle. Why do you change the way you hold when you never experience a perturbation the way that you hold? And that's the third part of today's talk, and we'll get to it at the end. Hopefully I don't have to talk too quickly to get there. All right, so question 1, how does the brain learn from the occurrence of a single error? And so I'm going to just walk you through a first principles reason why the brain might learn in this way. And this was an idea that came about in the 1980s, actually. And so imagine you're making a movement, and this is what the robot's doing to you. And so in the first movement, the robot produces no force to your arm, and so you're just free to move. And because of that, you just move straight to the target. Should be pretty easy. Then on the next movement, what happens is the robot now generates a 1 Newton force on your arm. And so you're not expecting this. And so this straight line trajectory is now going to curve downwards because you didn't expect those forces. And so at some point during that reaching movement, though, your sensory processes kick in. You say, I'm not longer on track. I need to produce forces, corrective forces upwards to get back to the target. And so you can sort of take these this force patterns and decompose them into 2 things. One is our feed forward commands. These are the commands that I'm showing in black here. This is what you thought that you needed to do to move to a target if you didn't have any errors, if there was no perturbation. Then there's this corrective bit. There's this red bit. These are feedback responses. These are the responses that your brain makes online while you're reaching when you're having an error that's preventing you from reaching your goal. All right, so on the third movement, if your brain was really smart, what it would do if it wanted to perfectly move straight to the target, expecting that it's going to experience this environment again, what it would do is it would basically produce upwards forces, right, in addition to the forces that move it to the target. So it might look something like this. And that would let you move straight to the target while compensating for the forces the robot's applying. And so what you can appreciate here is that these forces that the brain has added to the way that it moves from the way that it first moved are the same as the forces that it added when it was correcting for the error. And so one way the brain might learn is by taking the way that it responded to an error, its feedback response, and then copying that into the way that it moves in the future. And we're going to evaluate that possibility. And so we're not going to look at forces, but what we're going to do is we're going to record a higher dimensional signal. So we're going to record the activity of muscles in the arm while they're doing this task. And we're imagining that those EMG signals, or electromyography, basically muscle activity, is the sum of these feed-forward commands and these feedback commands as well. And so the question is, does learning, the change in this feed-forward response, the change in the way you think that you need to move, does that look anything like the way that you responded to an error, the feedback response? And so the way we study this is a triplet trial progression. So we'll do an air clamp, a force field perturbation, and then an air clamp trial. And what air clamps are is that while you're reaching to the target, the robot's applying any forces in the perpendicular direction to make you move straight. So you can push as much as you want along this axis, and you're not going to move anywhere except straight. And this is our way of, the reason why we do this is it's our closest way of trying to make you move with 0 error. And why we want to do that is if we think you have no error on an error climb trial, there's no response to that error. There's no feedback response because there was no error, it was 0. And therefore, the EMG that we record on these trials, we think is the closest we can get to that feed-forward estimate, what we think your brain is trying to do in the absence of error. All right, and so this would be the recording from the tricep during this first error clamp trial, and so it has some activity while you're making a reaching movement. That's the first error clamp trial, and this is the second error clamp trial, shown in blue. And so you see they're not the same. There are some changes here, and what those changes represent is learning from a single error. Even though you're moving your arm along the same exact path, the way that you're using your tricep to accomplish that movement has changed. And so the change from the first error clamp to the second error clamp, or the change in this muscle's activity, is the way that it learned from the error. And that would look like this. So it's basically blue minus black. And so there's this little negative portion followed by this positive portion later on. Now what I'm going to show you on this figure is the response to that thing in the middle, the perturbation. And so this is what the tricep did while you perturbed it. This is what happened during the movement error. And you see it looks very different than what it did during the movement, right? And what I'm going to do is plot this trace, basically the feedback response on this learning response right here. And what you see is this green trace. So this is how the brain responded to an error. In purple is how the brain learned from an error. And I think what hopefully you can appreciate from this single subject is they look very similar to one another, just sort of shifted in time. So this isn't just true of this individual and this tricep muscle. If you look at muscles, and this is now across the different subjects that we've recorded, these are recordings from the pectoralis while you're also making a reaching movement. This is a muscle that responds to a perturbation with a positive response. It excites the muscle. And if you look at learning in that muscle, you see a very similar profile, but just earlier in time. And if you figure out what the best shift that relates these two muscles together by cross-correlating them, you can basically shift these and align them in time, so you can see this really nice temporal correspondence between feedback and learning. And that's not just true of muscles that respond positively. If you take a muscle like the posterior deltoid, which has a negative response to error, you can also see the learning looks a lot like that response, just shifted in time again when you nicely align them. All right, and so there's really two models that could produce such a thing. And so of course correlation doesn't imply causation. So it doesn't necessarily mean that you get learning from feedback just because they look similar. It could be the case that you have a sensory error, a perturbation, that changes your feedback response. That's clearly the case. And it also somehow is driving the learning response through another process we don't really understand. And it's just because they're driven by the same error that they look similar, even though they're not causally related to one another. The model that we're talking about is one in which a sensory error causes a feedback response, and it's that feedback response that teaches the learning response. And so the way to disentangle these two things is that if you ever saw a difference in learning, if you measure two different learning responses, what this model would say is it had to be a difference in error. But if you saw a difference in learning responses here, this model would say it has to be a difference in the way the feedback response, independent of that error. And so what we did is we recorded, this is from the bicep, and we took trials where the bicep had a large response to error. So this is a large feedback correction, and then it had a smaller activity that's a feedback correction. And critically, the difference between these two trials in terms of what the arm did, in terms of this error, there was no different. And so if you look at how far the arm was pushed in visual space, it was no different when the bicep had a high response or a low response. And then when you look at the learning, so what that basically means is that if you see any difference in learning here, it's probably not because there's a difference in error, because the errors were similar. But when we looked at the learning responses, we saw that when the bicep had a large feedback response, the learning response also high, and similar for the lower gain, right? And so it seems more consistent with this idea, that the way the particular patterns we produce when we learn looks a lot like how we responded to the error in the previous trial. And it's not just true of the biceps, you could also see in the pectoralis. And I'm going to move on in the interest of time not to belabor the issue. So just a quick summary of this first part here. When we experience an error during movement, we not only correct for that error during the movement itself, which is a feedback response, we also did change the way we move in the future, which is what we're calling learning. And learning is really what we're going to focus on today. Here we showed evidence that's consistent with the idea that the brain uses a feedback response, the way you corrected for something, as a model for how it should do that same action in the future. And so on trials where the muscle had a larger response to error, it also had a larger response when it learned. And of course, this is not mutually exclusive. So exclusive of any other possibilities. So this idea that you learn from your feedback responses is probably accompanied by many different mechanisms the learning your brain can do. So for example, if you will, if you move really quickly to a target, you're moving too quickly so that you don't have enough time. Your sensory delays are too long to actually make a feedback response. You still learn on these trials. So even when you don't make feedback responses, you still can learn. And so we know the brain doesn't need to make a feedback response to learn, but it may be the case that when those responses are available, somehow that affects or shapes the way that it learns. That's one way to potentially think about it. All right, and so in the second part of the talk, we're not going to talk about learning from a single error. Now what we're going to do is we're going to repeat errors many, many, many times, over and over and over again. And we're going to study how the brain changes its response to error over time. All right, and so to motivate this idea, I'm going to show you a really simple paradigm. This is just a simulation of what it might look like if you're doing this experiment. So I just showed you forcible adaptation. This is what we would call visual motor rotation. And so subjects are told to move a cursor, this black dot, from a red starting position to a green target. And while they're doing this, they're first going to do it. It's going to be easy. Every time they hit the green target, they're going to get a point added to their score. But at some point, we're going to play around with the subject. So the first few trials, there's basically no perturbation what the subject's doing. But later on in the experiment, what's going to happen is we're going to impose a perturbation. And what the perturbation is, the subject's going to reach straight, but the cursor is going to be decoupled from the hand. It's going to be actually rotated off to the side. So when you reach straight, the cursor goes off and you can't hit the target. And so the brain has to learn is to adjust the angle that your arm is reaching in order to hit the target with the cursor. And so it might look something like this. These are the baseline trials where an individual is nicely, the cursor's tied to the hand, then you impose this rotation, they're reaching straight, the cursor's rotated, and they have to learn then to move their arm off to compensate for that rotation. And so what that learning process might look like is this plot right here. And so what this is it's tracking that angle that they're reaching relative to the target as a function of the movement. And so as I told you very early on, adaptation is a gradual process. You don't just turn on a perturbation on the next trial, you know it all. And so what happens is people gradually adapt to this perturbation over time. And so the larger numbers mean that they are rotating their reaching angle more. All right, but the interesting thing that I actually want to tell you about is if you then wash their memory out, so you bring them back to the baseline condition, and then you re-expose them to that perturbation, the same perturbation they had the first time. What happens is a phenomenon known as savings. And what savings is that when you experience an error that you've seen in the past, you actually change the rate at which you learn. And so that second time you learn from the perturbation, you learn faster. You can appreciate the difference between these two curves here, right? This also works in the opposite direction, right? And so the opposite of savings is something called interference. So if you experience an error where you saw errors in the past where they were opposite, this is like as if you were rotated not in this direction, but you rotated in the other direction in the past. That doesn't speed the rate of learning, that actually slows down the rate of learning. And so depending on your experiences, you can actually change the rate at which someone learns from a perturbation. If they did similar things in the past, they'll learn faster. If they did dissimilar things in the past, they'll learn more slowly. And we want to understand this process. What is fundamentally changing about the brain that causes you to learn more quickly or more slowly? And to get there, what we use are these models of error-based adaptation. These are called state-space models. And we're going to form this model together. So hopefully you have a grasp of what I'm talking about. And so people come in, and first what they're doing, we're plotting here their behavior. This is what they're doing, they're reaching. And so normally they're just reaching towards the target, and they do this over and over and over again. And so if we're going to call a movement X, and so X is your movement. And so normally what happens is X on trial n+1 is the same thing as X on trial n. So you just keep doing the same thing you did in the past. But then what happens is we introduce a perturbation, and that perturbation causes there to be an error. You're no longer hitting the target. And so this error drives the process of learning. And so you change your behavior when you experience that error. And so we need to add something to our model. We don't have error-based learning. And so this term accounts for error-based learning. We have our error here, and we have what we know as error sensitivity. And error sensitivity is a really important term. I'm going to use it for the next like 20 minutes or so. And what error sensitivity represents is essentially how sensitive you are to your error. Like how much are you going to learn from that error when you experience it? Okay, but we're not actually done. And so if we take our errors away, if you force errors to be 0, what we see is that behavior doesn't just stay there, it actually decays. And so there's also this process of forgetting, which is not in our model right now. So if we take the error away, we need to basically make our behavior decay, and we do that by adding a retention factor. And this is a number that's generally less than 1. And so if you don't have any error, your behavior decays exponentially. This is what everyone does. This is what you would do if you came into lab. Okay, now I'm also not done. If you came into lab, your behavior would never look like this. What it would actually look like is something like that. And so people don't just move nice and smoothly. They have very noisy movements, right? And so you can't produce the same exact movement every time you want to. And there's also noise in the process of learning and noise in the perturbations that you experience. And so you have to add in a noise term to this model, something that you can't fully model, but you know something about what the noise generally looks like. And these term is actually really important, and though generally we don't realize that. And I'd like to illustrate why it's important. So let's say you came to the talk today, you braved the coronavirus, and you decided to come to the talk, which is in the trailer building today, and to get here, you used the GPS. And you wanted to take some measurements to figure out where you were in order to get to the trailer building. So the first measurement you got from the GPS is over here, which is clearly not there. And if you believed to be exactly where you were, you would just stop there and be like, oh, I would use that path to get here, and you might not arrive the right way, right? But if you took another measurement in GPS, you'd realize, oh, it's a noisy sensor. I'm actually over here. And you take another measurement, it's over here. You're jumping around. And so if you're smart, what you might do is you might say, well, maybe I'm somewhere in the average of those things. I really believe that I'm here from these measurements. And you see that this point is very different than that point. But if you didn't know there was noise in your measurement, you wouldn't know where you were. All right. Now, if you're in the Albert family and you're navigating, you wouldn't just use one GPS. You'd probably use 2 or 3 in a car, which is rather frustrating. But anyway, and if you then took, you know, different measurements, you might measure here, here, and here from the second GPS unit. In that case, you might believe to be here. And the way I've constructed this problem is that, well, if you combine your 2 measurements together, you might be right where you want to be. And so the idea here is that it really matters to not know that your behavior is noisy, but it also means that you not have to appreciate differences in noise sources. All right. And so a very simple model of behavior would be, I have a noise term that includes things like movement and learning and the perturbation. But what actually we generally do when we fit behavior is we don't realize that we make a different assumption. And the assumption we make is that the underlying process of learning has no noise in it, but all the noise comes from our measurement, like the experimenter's measurement, like it's in my computer. Like they're perfectly straight, but my computer is adding all this noise to it. And that's probably a bad assumption. And that can get you into some hairy situations depending on what you're trying to do. And so what we spent some time doing in 2017 was figuring out a better way to fit these models, given the common types of experiments that we do today. And so we adjusted this algorithm that's called expectation maximization. The details aren't really important, but the idea is that what this does is it finds your A and your B, your retention factor and your error sensitivity, what we really care about, while using a model that looks like this, versus what we generally do when we try to just minimize squared error, which is a really typical way to fit data. What we're doing is we're finding A and B, but we're trying to maximize this model, which again, like I said, can get you into some bad situations depending on how complicated your model is. Okay, and so I can show you really briefly that it's important to use one or the other. So in simulation, you can simulate what learning looks like when you have an abrupt perturbation or when someone gradually learns something. And you see is that when you use this EM algorithm over this other algorithm that we generally use, you actually are much better, you have much lower error in estimating, let's say, the retention factor, but also your error sensitivity or any other thing you might want to be measuring that's included in your model. Okay, so let's get back to the important part, but first a quick summary. So when we experience an error during a movement, we change the way that we move. And that when we repeatedly experience error, it causes this prolonged adaptation. And then when we lose that error and we have absence of error, our behavior decays. And so we think that the process of learning is this competition between error-based adaptation and forgetting. And one of those depends on error sensitivity, and the other one depends on retention. And we're going to basically talk about these terms for a bit. And what we're going to do is we're going to estimate these 2 terms of our model while using that EM algorithm that has a better model for noise. Okay, and so by doing that, we're going to try to understand back to the very beginning of this whole like rant, and that is how when you do savings and when you have interference, like what is actually changing about the learner. We're going to use this EM algorithm. All right, so to reiterate, we're studying this process where you have 2 perturbations of the same type of exposure, and you learn more quickly the second time, versus when you have a dissimilar perturbation in the past, you learn more slowly the second time. And we want to understand, based on this model of behavior, are the changes that we see here, if you fit your model to different periods of behavior, is it caused by a change in error sensitivity? Are you changing how sensitive you are to your error? Are you changing how you forget that what you learned, or is it both of these 2 things? All right. So first, we're going to talk about interference, and this is a result of a collaboration we had down with Valeria Della Maggiore and a student of hers, Gonzalo, down at the University of Buenos Aires. This is a virtual collaboration, nevertheless quite fun. What happens in this experiment, I already talked to you about it, is that you're going to have a perturbation A. Then what Valeria did is they put a break, so you actually wait a period of time, and you come back and you go into the opposite environment. So these are 2 opposite perturbations that you're going to experience after a break in time. And what your behavior might look like is this. And so this group learns from the first perturbation, then they have a 5-minute break, they come back, and then they learn the other perturbation. And so you see as a result of the break, there's a little bit of forgetting. You move back towards your baseline, and then you learn from the other perturbation. And what's shown in black here is this is a control group that never experienced the A perturbation. So this is what learning in B would look like if you never experienced anything before it. What we want to know is, by experiencing A before it, does this somehow change the learning process? And so you can compare these 2 traces by nicely aligning them in time, and you see indeed that when you experience A in the past, it slows down how fast you learned. Now, what happens if you waited 24 hours? So now, instead of just doing B right after A, 5 minutes later, you're gonna wait 24 hours. And what happens here is that there still might be a little bit of a slowing of learning, but it's much better. And so the longer you wait after the experience of dissimilar errors, the better you're gonna do when you experience the dissimilar environment. And again, what we're gonna ask is, are these changes caused by changes in retention, changes in error sensitivity, or both, and with using that EM algorithm? And so first I'm gonna plot as a function of time, this is the 5-minute break, the 1-hour break, up to that 24-hour break, and the control group that never experienced A, how their forgetting looked like during this B period. And we see that there was no change there. But if we look at error sensitivity, what we see is that all of the difference in their behavior was explained by error sensitivity. So basically, when you experience a perturbation really soon after you experience an opposite perturbation, it slows down your learning rate by making you less sensitive to your errors. But the longer you wait, the more this recovers. And after 24 hours, it's almost exactly the same as control, though it's likely still a little bit small. Okay, now I'm gonna contrast interference with savings. So savings is the opposite. You're gonna get a perturbation of one type, and then you're gonna learn from it, as we've talked about many times now, and then you're gonna get the same type of perturbation again, not an opposite perturbation. And this is gonna make you learn more quickly. And so this is data from that vision motor rotation test. We also, to show you this is not specific to that type of learning, here's movements of your eye. So you can do this with walking or your vestibular system, lots of different things. But here's an eye movement, so you're moving toward a target, and the target is moved inwards, and over time you have to learn, the eye has to learn to make saccades of an amplitude that's actually smaller than the target initially sees. And so that process of adaptation looks something like this, and you can see the second time you experience it, it's also faster. And so arm movements, eye movements, they both show savings. What's the cause of it? So again, we're gonna measure retention and we're gonna measure error sensitivity. This model is a little bit more complicated, and I don't have time to talk to you about it today, but the idea is that you take that error-based model, and it's not just one thing that learns from error, there are multiple processes that learn from error, fast things and slow things. What you see is that in the context of retention, there's no difference in how the forgetting is affected in either these slow processes or these fast processes. But the only change that you see is that in this fast error learning process, that there's a change both for the arm and the eye. And so the reason why you learn more quickly the second time is because there are these fast states of learning that become even faster because they become more sensitive to their errors. And it's not something that we've just seen. This has been seen by other people, not necessarily using EM to detect it. Okay, so part two, quick summary is that when people experience perturbation, the rate at which they adapt depends on their prior experience. And when this prior experience is similar, they adapt faster, and when it's slower, and when it's dissimilar, they adapt more slowly. And we used EM to try to understand these changes in the rate of learning, and we found that it's caused by a change in error sensitivity, but these forgetting processes really don't seem to care what you did in the past. They just do whatever they normally do, independent of your past exposure. All right, and before I get to the final part of the talk, I'm gonna just mention one additional thing about error sensitivity, which is actually kind of cool. And so changing error sensitivity not only changes the rate at which you learn, it actually changes the capacity of your learning itself. So how much you're capable of learning if you do it for a very, very long period of time. And we're gonna understand why that is. And so if people come in, what we generally see is that you can perturb them and you measure their learning, but they never quite get to the perturbation. They never get to one. They never fully compensate for the perturbation experience. And so even when at some point they reach the steady state, we call it, where there's this residual error that you just can't quite kick. Kind of puzzling. But it turns out it's not that puzzling because the model that I just showed you predicts such a thing. And so we're gonna do a little bit of algebra to bring you back to grade school. But this is your error-based learning model. And so what we're gonna do, this model predicts this phenomenon. And so the first thing you do is you have to represent what an error is. And the error is, you can see right here, it's the difference between a perturbation and your behavior. So it's just this P minus X, right? So error is just P minus X. You substitute that in, and you have this expression. You combine some like terms, and then you introduce what is the steady state condition. And what this is that at some point, you're gonna reach a condition where what you do on every single trial is the same, over and over and over again. So x of n, and xn plus 1, and n plus 2, so on and so forth, are all equal to some steady state value called x steady state. You just substitute that in for your x's here, and you rearrange, and you get this guy, which is an important equation. And so what this is that your steady state learning is related to the perturbation you experience times some multiplier, which is your gain. And what you see here is that this gain depends on this B term, which is error sensitivity. And it also depends on the A term, which is learning. And so what you can think about qualitatively is what this equation represents is that the total adaptation you experience is a balancing act between forgetting and learning. So if you go back over to this plot here, you can see that when your processes of learning from this error that you just can't get rid of match exactly how much you forget over time, when these two things equilibrate, you just stop learning. That's at least the theory behind it. Okay, and so if you ever see in two different conditions that people learn a different amount, that could be because of two things, right? So if one case you see people learn less, it could be because they're forgetting more rapidly. Or it could be forgetting because they have a lower error sensitivity. And so what we want to do is find conditions where people learn different amounts and understand, is it because you forget more quickly, or is it because you're more sensitive to your errors? And we got kind of lucky that we looked at the literature and we found a nice condition that actually produces this thing. And so this is an example from the force field adaptation again. So people are moving and getting perturbed by these force fields. And what we do in one group is the normal thing. We have a baseline period and then we turn on a perturbation that's constant on every trial. And then we measure their learning over time. Just forget about the error clamp period, and I'll get back to that in a second. Just look at the learning curve now. Then we can measure what their residual error is. So this is just the difference between the perturbation, which is 1, and where they ended up, which is about 0.8. And so they have an error of about 0.2 at the very end. Okay. Then what we do is we have another group that has a perturbation that's not constant, but it's noisy. It's variable from one trial to the next. Critically, it's the same mean as this perturbation. It just has a bit trial-to-trial variability. So it has the same average driving force for learning, but different statistics to that process. And what we see is that by adding variability, there's this really robust effect on learning. It actually decreases the amount that people learn in the long run. And so it increases these residual errors. And so this is in force field adaptation. You could do the same thing if you do these rotations that I showed you that some simulation before. So if you compare a no noise perturbation to a high noise perturbation, you can also see that it significantly impairs your ability to adapt to that perturbation, or increases your residual error is the dual statement. And you can actually do this really interesting causal thing. So you can adapt someone to a noise-free perturbation, and so they learn, this is their learning curve, and then you could add variability to the perturbation. And even though they've learned to 25 degrees here, actually by adding variability, they forget a little bit. So instead of continuing to increase, their asymptotic learning actually drops after you add variability. And it's a really robust effect. Like every single person you do this to, they'll show this, at least as far as we did it. Right, so remember, again, this could be happening for two reasons, right? So maybe it's the case that by adding a lot of variability, people are not really retaining what they learned, so they have for higher forgetting, or it might be they're getting less sensitive to their errors. And so we're going to evaluate these possibilities. So possibility one, again, is that you have difference in the total amount of learning because there's higher forgetting. And so the way that we measured that is we took these periods, right? And so there's these periods at the end of an experiment where we take away your errors, and we just let behavior decay, as you can see in this gray strip right here. And that gives you a measure of what someone's forgetting rate is, how fast their behavior decays. And so here I'm just plotting that in 3 different experiments, normalized to how much they were adapted. And so this is the decay process you could see in these error-free periods. You see that there's generally no difference in them. And if you actually look at what the rate of this exponential decay is, the retention factor, you see that in any of these experiments, there's no difference in how fast people decay. So it doesn't seem that the variability and the perturbation affected their decay rates at all. However, you can contrast that with error sensitivity. So what we're going to do is we're going to calculate the error sensitivity in every single trial. How much did you correct for the error you experienced in the previous trial? And so unsurprisingly, given what I've already told you, if it's not here, it has to be an error sensitivity. So for all the experiments, we see a very large difference in error sensitivity, which is the same thing that you saw change in anterior grade interference and savings, right? But it's not in all errors. And so an error is not just like one constant, right? So you can have large errors, you can have small errors, you can have medium-sized errors, pick your error, you can have. And what we actually saw is that when you break it down as a function of error size, that error sensitivity is only different for these small errors, but it's not different for the larger errors. And so why might this be the case? And so it turns out that there is a model that our lab previously put forth that actually nicely explains this as well. And so imagine you're making a movement, and on trial end, you reach off in that direction. You have what I'm going to call a positive error. And so you learn from that error, you correct it, and you're going to make another movement on trial n+1. And you get closer to the target this time, but you're still not quite there. And you have another positive error. What this is a signal for your brain is that you didn't correct enough for the first error. You actually could have corrected more, and you would have hit that target. And so what that might mean is maybe the brain should increase its sensitivity to the first error. The flip side is, let's say you have this error in the first trial, but you overcorrect on the next trial. Your error goes from positive to negative. And what that means is that you corrected too much. And so you're too sensitive to the error. You might want to decrease your error sensitivity. So maybe what's happening is that when you add variability to a perturbation, it's making you have more inconsistent errors. and that's causing your error sensitivity to drop. And that might be the explanation we saw in the previous slide. And so the details aren't so important here. There's lots of different experiments we did, but the result is the same for each of them, and that's that when you have a variable perturbation, it makes it more probable to have inconsistent errors. It makes it more probable to be in a situation where it makes sense to decrease your error sensitivity. And what's even more important is that if you plot this as a function of the error size, it looks like this. So for large errors, adding variability to your perturbation doesn't make it more likely to have inconsistent errors. But for small errors, it makes it more likely to have inconsistent errors. And if you compare this with the error sensitivity, you see that they look very similar to one another, which again is just correlation again, but it suggests it's possible that these changes in consistency are what are driving the differences in error sensitivity we see here. All right, now last but not least, this is a bit of a side before I get to the final part of the talk, and I mention it because it's interesting, and we're doing some follow-up experiments on this right now. And when I first got to lab, I was a bit confused because I'm from chemical engineering, and so we're talking about neuroscience and learning, and I just thought that when you experience a perturbation, like you were just strategically adapting to it. So in the next trial, you just like kind of knew, oh, this happened to me, I'm going to do something else in the next trial. And it turns out that that is part of what happens when you adapt, that you are able to see what's going on and change what you're trying to do. But there's this other bit of adaptation that we call implicit adaptation. This is adaptation that you're saying, I'm trying to move straight, but my arm didn't move straight. And that's because there's a subconscious learning mechanism that made my arm not move straight because it's learned from errors, even though I didn't want that to happen. Or maybe I wanted it to happen, but I wasn't necessarily commanding it to be so. And so there's these strategies and then these implicit adaptation, right? And so when we measure these differences in total learning, we don't really know if it's because of a change in how people were strategizing, like where they were trying to aim their hand, or where they were implicit memory was, like how much they learned. And so one way to try to ask that question is you can tell the subjects, you can try to get rid of this explicit bit. You can say, listen, I want you to try to take your hand and I want you to move your hand straight through the target. Forget about the cursor, there's no rotation, there's no tricks, move your hand straight to the target. And what you're gonna see is when you tell someone to do that, their behavior really fast, quickly drops in the next trial, and that's because you get rid of any strategies they have. And so that drop is what is basically, we think, is this explicit memory. It's basically how much they were aiming. And what remains after that drop is what we think is implicit memory. It's like what the part that they can't do. They're trying to move straight, but their arm just doesn't move straight. That's the implicit memory. And what we see is that, you can see it from the plot here, but that actually the only difference we see in the asymptotic learning here is only in this implicit bit that you don't control, but the amount that you're aiming is the same in both conditions. And so what we think is we found a manipulation, this variability that specifically affects these implicit subconscious learning mechanisms without changing the explicit angles. And I have other data to speak to that as well, but I don't have time to go through it today. There's another way to try to measure this. You can ask people to tell you where they're aiming their hand, like what they're conscious of doing. And that way you can try to measure this directly, this explicit angle. And again, what you see here is that it doesn't seem to affect where they believe they're aiming their hand to. It actually is the same across both conditions. All right, so just to summarize part 2 before we get to part 3, is that when people adapt their perturbation, they reach a limit where their performance stops improving. And that when variability is added to the perturbation, that total adaptation limit drops. And that much like savings interference, we see that the quantity that's really important for determining how much you learn is this error sensitivity and not this retention factor. And that we think that error sensitivity is modulated by the consistency of the errors that you experience. And that this is potentially done by a subconscious learning system like the cerebellum. All right, and finally, last but not least, we've talked only about movement perturbations now and about how those perturbations affect your movements. We haven't talked about how they actually affect what happens after you move while you're holding still. All right, and so I showed at the very beginning of the talk that it seems that when you have these perturbations that never affect holding still, it still nevertheless changes how you hold still. And we're gonna ask why that might be the case. All right, and so these are people that are, again, moving between 2 points in space. And when they get to the target, there's this 2-dimensional clamp that holds their hand there. And the reason why we're doing this is we want to allow people to apply forces at the hand without the hand moving off the target. And that'll become clear why we're doing that in a second. And on some draws, we put them in that channel condition I told you before, that air clamp. So they're going to reach between the starting point and the target, but the robot is going to create forces in the perpendicular axis, so it makes you move straight. And so no matter what you do, no matter how you push, left or right, you see that the reaches are virtually the same. So this is a 2 millimeter displacement for a 10 centimeter reach, so really tiny X displacements for a really large reach. Okay, so even though the hand is moving along the same path, you're able to produce forces that are perpendicular to that path. And so these are 3 different trials where you're producing 3 different sets of forces that in one subject. So on some trials, that participant pushed up or really to the right. On some trials, they pushed down or to the left. And some trials, they actually, in the middle of the same movement, they pushed left and right. So this is during the reach. But they also, even though we didn't tell them to, they also pushed on the handle differently when they were holding still. And so when they pushed to the right, they seemed to also push to the right when they held. When they pushed to the left when they moved, they also seemed to push to the left when they held. And when they did both these, it seemed that they sort of canceled each other out. And so what it seemed to us is, sorry, before I actually get to that point, if you average across lots of movements, you can get rid of this variability and you see like really strong relationships. And so on trials where you reach upwards, you have forces upwards, and trials where you reach downwards, you have forces downwards. So it's this really robust correspondence between moving and holding. And so holding forces we see here occur even when you never experience perturbation. So the first forces I showed at the very beginning of the talk, if you remember back to then, was because you adapted your force field. These are just normal reaching movements that you put in channel. So the holding forces don't necessarily come from learning. They just are present all the time. And it appears that, I just mentioned that bit. And so what's possible is maybe what's happening is that the holding forces are coming from the way that you moved. When you push to the right, you continue pushing right to your hold. And so maybe part of the way that we hold our arm still is actually determined by the way that we move. I'm gonna explain what I mean by that. And so I think most of you would be familiar with the idea of distance is equal to rate times time, or D equals RT. Ring a bell? And so in other words, the amount of miles you might move in a car is equal to the speed at which you're moving miles per hour times the number of hours that you're moving, right? And so if you're moving 80 miles per hour for an hour, you go 80 miles. So what this means is that if you know how fast you're moving and how long you moved, you actually know where you are, even though you never had to measure it. You didn't have to turn on your GPS. You're like, oh, I know I moved 80 miles. I was going 80 miles per hour. You can plot that, right? You can plot your speed as a function of time. So you're going 80 miles an hour for 1 hour, and then you stop. How far did you move? Well, actually, how far you moved is the area of this rectangle. And so if you just multiply 80 or 1 or 80 by 1, you get 80. And so the idea here, the principle is that you can calculate how far you moved by looking at the area under a speed versus time plot. So if you just look at the area under that curve, you can actually see how far you moved. So it works not just with these like really nice constant movement speeds. If you have an irregular speed, you can still calculate the area under this curve. But if you remember from calculus 1, what you would use is an integral. And so an integral is the mathematical quantity that calculates areas under curves for you. And so you can figure out the distance you moved by integrating your speed. And so why am I telling you all this? When I'm telling you this is that in principle, what is possible is that if your brain knows how fast it's moving and can integrate that quantity, it can know where it is in space without having to measure it. And might seem kind of weird, that is more or less what we think that your eyes do. So this seems to be the way that you control your eye movements. And so I'm going to show you some evidence that we certainly didn't collect in our lab from this particular literature. And so what I'm showing you here are your eye muscles. This is what lets you move your eyes back and forth. And these are the neurons that make your eyes move. And so this is what those neuron activity looks like. So here's an eye movement, and here's where it holds still. And what you can see is that that neuron has activity here in the center period. That is moving activity, and it also has holding related activity. So you don't get holding for free. Holding requires energy. If you try to keep looking outwards, you feel your eye muscles get tired. That's because your muscle tissue is trying to pull your eye back in the center. And so you have to have holding activity. Okay, so you can record from neurons in the brainstem. So these are neurons that are one synapse away. So if you go back one, you find out what tells the motor neurons what to do. You can find these neurons that are called excitatory burst neurons. And these are neurons that fire only when the eye moves. So this is a movement trace, and you see when it holds, the neurons stop firing. They only care about movement. But here's the surprising thing. If you take an electrode and you don't record from these neurons, but you stimulate them really briefly, if you have a brief stimulation, what happens is the eye not only moves, the eye actually holds in time. And so the question is, why should stimulating neurons that only care about movement produce both moving and holding? And the answer was figured out by a scientist actually here at Johns Hopkins named David Robinson, who unfortunately passed away. But the answer seems to be that these moving neurons, they encode the velocity of the eye, kind of like that miles per hour in the previous example. And those commands move the eye. But they don't just go to the eye muscles. They actually go to another set of neurons in the brainstem. And this is actually called the prepositus. And these are neurons that, rather than having no activity during holding still, they have activity that ramps up and then maintains during holding still. And if you look at what these neurons encode, if you record from them, these neurons, their activity is linearly related to eye position. And so what these neurons are doing is they're taking a velocity command and they're getting a position. And so it's literally that integration I showed you on the previous slide. These neurons do mathematical integration. So David Robinson called this the neural integrator. And so what we're going to ask is, maybe this is what's happening for the reaching movements. So maybe by pushing to the right while you're moving is being integrated into believing you're a little bit to the right when you're holding still. Okay, so first of all, it seems kind of a crazy idea. So the arm is a really complicated object. It's a lot more complicated than the eye. And so we needed to know, is it even possible that if I look a movement from here to here, that if I want to understand what my muscles are doing when I'm holding still, that I can compute that from integrating what happened when I moved. And so to ask this question, we linked up with Mark Churchland over at Columbia and a student of his, Andrew Zimnick, who provided us some data and had trained a monkey to make movements from a center position out to different 8 targets on this vertical screen. And so what that looks like is a monkey is going to hold their hand at the center position. And what this is here is it's the activity that we're recording from the from the anterior deltoid. It's a muscle for the arm. And all of it is the same at the very beginning because they're all at the same point in space. And now they're going to make 8 different movements that are color coordinated, so you can see the different movements. So this is the reach to the outwards target. So it's from center out. And what you see is that the anterior deltoid is more active in some conditions and less active for some reaching directions. And then it has the sustained holding activity at the very end of the movement. They're going to hold here for about half a second, and then they're going to reach back. And so there's another reaching movement where this phasic activity happens, and then they hold still at the end. So they have this constant activity. And so essentially what we have is we have 2 movements. We have a reaching out movement, reaching out activity, holding activity, and we have a reach back movement. We have reach back activity and hold activity for the reach back. And we want to know is, does this integration function model this problem? And so what I mean by that is if I look at the change in the hold activity, so basically this versus this, does it look like the integral of my reaching activity, which is just the area under this curve? And so for both the monkeys that they recorded from, monkey A and monkey B, what we saw is that if you integrated reach pre-activity, it actually did a pretty decent job of predicting the change in hold activity. About 50% of the variability in hold activity can compute in this way. And so even though the arm is really complicated, to a first order approximation, you can integrate the way you move and use that as a signal that helps you hold still at the end of that movement. All right, again, correlation does not imply causation. And so what you'd really want to do is test a stronger prediction. And that's that, let's say you move to the same point in space on different reaching movements. What the integration hypothesis predicts is that if you change the way that you move to that same point in space, you'll also change the way that you're holding there. Now, it's hard to test that idea with arms because there's lots of different joints that could be varying when you're holding at one point in space. And so we try to look at this in another more simple movement, and that's actually movements of the finger. And so we teamed up with Stuart Baker over at Newcastle in England and a student of his, Demetris Soteropoulos, who trained a monkey to basically move their index finger and track a visual target on a screen. And so what that looks like is this. The monkey has their finger in this tube, and they push the tube down to basically track the motion of a cursor. So it starts in one position, it moves for a second, and it ends in another position. They have to hold there. So there's 2 hold periods and a move period in the middle. All right, now what happens? So the monkey is really well trained, so they do roughly the same thing every single trial. But if you record activity from the muscles, the thing that are making the finger do this, it actually is really noisy. And so this is activity from one of the muscles. This is one of the flexor muscles that allows the finger to do this flexion movement. And you see for those same 5 trials, which look very similar, the muscle actually did very different things in each of those trials. Sometimes it was really active, sometimes it was less active. And so when you look at this high variability in the hold activity, and you compare that to what is very little variability where the finger is. So this is the first hold position, this is the second hold position. You say, well, maybe it's really variable because the finger's in a slightly different spot. And so you can ask, how much of this variability in the hold activity can I predict from variability in the reach activity? This is just linear regression. And the answer is very little. So you can actually only count for about 1% of the trial by trial variability in that muscle from looking at where it is in space. And so maybe the other possibility, integration, is that maybe all this variability is not coming from where it is, but how it moved there. And so we're going to integrate the moving activity and see how we can predict the holding activity. And of course, given that I'm telling you about it, it works out. So if you integrate moving activity and you ask what the change in holding activity, now you can make sense of that muscle's activity. Now it actually makes sense what that muscle did on a trial by trial basis because it had trial by trial variability. And if I show you the data for 9 different muscles in both monkeys, these ellipses represent like a distribution of like thousands of trials. What you can see is that for both monkeys and all of their muscles, that the way that they moved significantly affected the way that they held still in this integration manner. Okay, so quick summary before we get to the last, like the final part of the talk, hopefully 3 more minutes, that when you do reaching movements, the integral of your reach commands predicts change in hold commands, and that's irrespective of how you reach. That's what we saw in the monkey. Reaching movements. Then we looked at finger movements, and we saw the same is true for trial variability, which moved us closer to this causal argument, but doesn't really quite get us there. And one of the problems, of course, is that the variability that we saw was internally generated by the animal. So when you're trying to do a causal experiment, try to figure out if this causes that, what you want to do is have an outside party make the animal change their behavior, not let them internally change their behavior. That's a better test of causality. And so the way that we're going to do that for the next few slides, and just to the end of the talk, which is about 3 slides, is we're going to use the force fields again. So we're going to make you change the way you move by putting a force field on your arm. And we're going to see, even though we never changed the way that you held, we're going to see how you hold at the end of it. All right, and so that looks something like this. And so people are going to gradually adapt to a perturbation. We're going to perturb their arm with this force field. We're going to gradually increase that over time. And on every few trials, we're going to measure the forces that they're producing in this error-free channel trial. So we're going to measure the forces you produced during reaching and during holding. And what it looks like is this. So the colors here show you where you are in adaptation. So 0 or blue is you aren't adapted, and red is like you're fully adapted. So this is like the trial by trial learning. And what you see is that the reach period ends at about 0.5 seconds here. And so you nicely learn to compensate for that perturbation, but you also change the way that you hold. And so even though you were never perturbed at the target, you also increase your holding activity the way that we expected you to do if you're integrating. And if you take that perturbation away, if you de-adapt them, the holding forces then go away. And if you do it in the opposite direction, the same thing happens. You just flip the sign. All right, so again, the question is, can I predict holding activity from the integral of moving activity? So we showed the equation for EMG. Now I'm showing it for forces. The change in your forces should be the integral of the force in the reaching period. And so can you predict the change from here to here by integrating this? And the answer is you can. And so each of these points here is an average across many people. And so the relationship is actually really nicely linear. But if you look trial to trial, it's actually a lot, it's similar to the EMG data I showed. It's about 50% of the variability trial to trial. Okay. So quick thing you might want to test here is we're saying that we think the holding force is caused by an integral of the entire moving force. But maybe there's a simpler case. Maybe it's just that the holding force is a continuation of how you moved. It's not an integral of the whole thing. It's just, oh, you keep pushing in this direction when you're pushing like that just before you ended your reaching movement. And so to test that idea, what we did is we had people reach between 2 targets. We perturbed their motion during the second half of the reach. And people increased their moving forces, which is shown in green, and their holding force is shown in red. That's the same thing I showed you in the previous slide. If you continue just to perturb them during the second half of the reach, they just keep doing the same thing more and more on each trial. What we do is we contrast it with a different condition. So here we have the second half perturbation here, but then we add a first half perturbation, a perturbation that pushes you in the opposite direction. And what this is really important is that you're still going to be doing the exact same thing before you end your movement. You're just changing what you did earlier in the movement. And more importantly is that what's kind of cool about this is that if you can do this, if you can learn to compensate for this type of perturbation, you integrate to 0 because what you did on this side cancels out what you did on the other side. So you integrate to 0. And so what we saw is actually as the integral of that movement went down to 0, so did the holding forces. And if you compare the activity, this is activity during the first phase. So reach just in one direction, hold also in that direction. But when you add that second perturbation, you learn to produce a negative force. And you see that even though you're producing the same amount of force just before the movement ends, you have less holding force because this is not a continuation of that. It's an integral of the entire thing. And so this is a little bit better evidence for this idea of integration. Okay, literally the last thing I want to mention to you is where might this be happening? And so here are data from the mouse, and this is from Adam Hanton's lab. What's really special about this mouse is that this mouse has been genetically altered so that you can shine light on that area of the brain, that motor cortex I showed you on the very first slide, that part that's affected by stroke. You can shine light on it and shut those neurons down. You can completely silence that area, more or less. And so what the mouse is going to do is it's been trained to reach out in the dark, grab this pellet. It's going to grab the pellet, and then it's going to try to bring the pellet to its mouth. But what the experiments are going to do is when they reach the pellet, they're going to turn on that light. And they're going to what you're going to see is the movement's going to stop. They actually can't complete the movement and bring the pellet to their mouth. And they're actually going to take their other paw, and it's kind of cute. They're going to actually reach, grab their paw, and try to rest their arm all the way up to their mouth to get the pellet. And so that's what you're going to see here. They're going to reach out. The laser comes on. They want to lick, they can't get it, and they reach with their other paw and they bring the paw up. And so why I showed you this video is not just for the cuteness factor, but is that when you turn the cortex off, what was interesting is that the arm stopped moving, but it didn't fall. Like, it didn't just stop. And so there was some other part of the brain that was clearly maintaining some amount of activity to hold the arm in place against the forces of gravity. And so what is that? It wasn't the cortex. And so to answer this question, to look into what this might be, we teamed up with John, who's back there, and Alkis, who's an awesome postdoc and friend of mine, who work with stroke patients who have damage to the areas of the brain that are similar to what you inactivated in that mouse. And like I showed you at the very beginning of the talk here, and so it shouldn't come as any surprise. At the very beginning, I showed you that when you have damage to the cortical spinal tract, it affects your ability to move, and so it makes your trajectories very erratic. But if you put people in those channel trials where you remove air and you just measure their forces, you see they have these really variable and large forces, but those reaching movements terminate in these really stable holding periods. And so the question is, even though the reaching forces are moving, are significantly adversely affected by the stroke, maybe the way that those forces are integrated into the holding period is not affected. Maybe it's normal. And so to ask that question, we integrated this and compared with the final activity. This is, you can actually see in a force field experiment, the change in hold activity is a function of the reach activity for basically healthy control shown in blue, the good arm of the stroke patient shown in black, and the paretic arm of the stroke patient shown in red. And what you can see is all these cases that having a stroke just doesn't seem to affect integrating reaching forces into holding forces. And if you look at just the within subject, basically integration gain in the slope of this line, you see that they're the same in all these conditions. And so what we think is that having a stroke doesn't affect integration. It's probably not being controlled by the cortex. Okay, so brief summary. We started off in part one talking about how you respond to an error and then learn from that error. And we showed that the way you learn from an error looks like how you respond to that error, learning from your feedback response. Then I showed you how you can model these learning processes with an error-based model that appreciates how you retain memory and how you also learn new memories from your errors that you experience. And we talked about how it's really important to include noise in those models. And by including noise and treating it appropriately, you can fit those parameters better that you care about when you're trying to understand what people are doing. We showed that using such an algorithm can explain why people have a slowing of learning, and that's a change in this error sensitivity that recovers in time. But also the opposite is that when learning accelerates, it's because error sensitivity seems to increase. And last but not least, error sensitivity also seems the critical thing that sometimes is what controls how much you even learn in the long run. Then we took those reaching commands and we looked at evidence in the monkey that suggested that these commands that, oh, at least I'm not plugged in. And we show evidence in the monkey that these moving commands not only move the arm, but they're also integrated by this other part of the brain, potentially. And that creates these holding commands. And I didn't have time to go into this today, but it actually turns out the way that you actually adapt your reaching commands, you can also adapt these holding commands, which, like I said, I'm not going to talk to you about. And that because this integration process wasn't damaged after you had a stroke, we think potentially that if such a thing exists, it may be located in a different part of the brain, the subcortical region. That's not the place that computes how you move. All right, I want to end with one last thing, a picture of a pretty famous person in neuroscience. His name is Henry Molaison. Some of you may have learned about him as HM. And why HM is really important is he taught us a lot about memory. And this whole thing was about memory. There were motor memories, but memories nevertheless. And actually, Reza got a chance a number of years ago to test HM before he had passed away. And what made HM very special and also very tragic was he had intractable epilepsy. And so there was a part of his brain, the temporal lobe here, that was removed to try to cure his epilepsy. But the problem is they took it out on both sides. And so he had this part of the brain called the hippocampus removed. And so he was unable to form new memories for pretty much the rest of his life. He had about a minute or so memory, with some exceptions. There's a person that studied HM who also passed away, but she used to work at MIT. Her name is Suzanne Corkin, and she wrote a book about HM after his passing called Permanent Present Tense. And there's a passage in the book that I thought is really nice and I'd like to end with. And I'll just read it to you. And so Suzanne writes, as I type these words, I wonder what exactly is going on in my overcrowded brain. How do my networks of neurons marshal together the pieces of complex technical information I have learned, synthesize them into thoughts and perspectives, and put the total sum into words my fingers are then directed to type? How remarkable that the brain can fashion simple sentences out of such chaos. We will never have a formula to fully explain how the noisy activity of our brains gives rise to thoughts, emotions, and behavior. But the magnitude of the goal makes pursuing it all the more exciting. This challenge attracts brilliant adventurers and risk takers to our field, and even if we will never completely understand the way the brain works, whatever small part of the truth we're able to learn will bring us one step closer to understanding who we are. And with that, thank you for your time. I'd like to acknowledge some people, but first, I know I'm a little bit over an hour, but if you have some questions, I'll take them before I do some acknowledgements. Simon? Oh. All right, well, if there's no questions, of course, you can talk to me afterwards. I'll just acknowledge some people. And so first, I just wanted to acknowledge the lab. And so if you guys haven't been down to our lab, we have a really close-knit, awesome group. I can't imagine having done a PhD anywhere else. Not only are these an incredible caring group of individuals, but they're also really smart. I don't think I'll ever work anywhere else again where such the caliber of individuals is so high and the kindness is also so high. And I really appreciate all their contributions to all of these ideas and their friendship throughout these last however many years. And the lab has shifted over time, but I just wanted to show you some various pictures of all the fun that we have. And this is actually just recently at Matthew's piece, and oh, I have one more. I have one more. So this is, oh, I have two more. This is really the last one. This is at the bus stop near Patterson. We just took this last week, I guess. So of course, in the head of our lab is Reza, my advisor. And so I have to, this is at a retreat. And so I just wanted to recognize Reza. Not only is Reza obviously a really incredible and capable scientist and mentor, but he's also just an extremely kind and generous person. And because of that, I always wanted to come to work, and all those terrible stories you hear about people that have terrible PhD experiences, that was not my experience. And I learned so much from Reza. Any success that I hopefully will have is because of what I've learned in his lab. I just wanted to say thank you, and I know we'll continue to be friends for the rest of my time here on Earth. I want to also talk to my friends, some of which are here with us today. So thank you very much for making the trip. I have friends I put on here from Lafayette, where I went to college, and people I've met here in Baltimore. I hope the pictures will show that we've had a lot of experiences together. And so not only have these experiences changed my lives, but you've changed my lives for the path that you've chosen and the things that I've learned from you. Yeah, I obviously really appreciate that. And I know that we will continue to stay close regardless of where we go. I think there are one or two more. I think there's one more photo of this. I just want to end with that. Oh, sorry, one more after this. In particular, I have to recognize two individuals that I spent basically 5 years of my life with here. And that's Nash and Bin, one of which is here today. And so Nash and Bin were my roommates up until recently. They all beat me at graduation. I won't hold that against them. But really, Baltimore would not be the same without them. I mean, like, we had a family, essentially, at 249 West 31st Street. And we did everything together, from music to shows to, you know, movies and what have you, as you can see from the pictures here. And I don't know how I wound up to living with probably one of the two most talented scientists in Baltimore, but somehow that happened. And I wish them luck, obviously, in all of their paths. I want to talk about my extended family. And so some of these people are here with us today. Some of them are, you know, far away in New York. And some of us, like my grandmother, have passed away recently. And my grandpa actually can't make it today because he's up in New Jersey, probably driving my aunt a little crazy. I have just an amazing family. You know, it is these moments of respite between, you know, these hard pushes when you're at lab and you're trying to figure out what's going on with people's movements, and you go back and you celebrate holidays, and you have such a supportive environment. And really, anything that I am done and the person I am is because of the people that you see on these slides. Recently, you can see some of these pictures. I've gained some more family up in Toronto because of Manat and the Maliks. Yeah, these are them. That's Atticus, who keeps me up at night, or us up at night a lot. On a similar vein, I want to thank Manat. And so Manat we've been dating for some time now, and really has become my partner here in Baltimore, and has really made this feel like a second home for me. She's going to be starting her PhD actually at UNC in August. And so I hope that I can be half as supportive to you as you've been to me over these past however many years. And I hope that these pictures represent just a small piece of the adventures that we'll continue to have. And last but not least, I just want to recognize my family, my immediate family, my mom, my dad, and my sister, who you can see in these photos. And so in the Albert family, you don't know us, we're very loud. You probably heard that, how loud as I was talking to you today. But we're also a very close-knit group. And in my family, if you ask for help with something, it's not like who, what, or why, it's like when. Like, when do you need it? Do you need it now? Do you need it tomorrow, next week? I'll come right now, you know, anyway. So, you know, some of the data you see in these slides are actually from them and the age match controls. But really, it just, I obviously would not be anywhere close to where I am right now without these people who have shaped me. And I appreciate, and I really want to dedicate this all to them. And thank you all for your time. Alrighty, well, I think there is some thing happening down in 3 floors down. If you have some more time to stick around, we'd love to see you downstairs on the 3rd floor. That's room 416. Sorry, 4th floor, 416. We didn't move. It's 3 floors down on room 416. And again, thanks for coming, guys. What? Oh, and thank you for all who tuned in online. Or I guess you can't see me, but thank you for tuning in. Is there something that I need to do to stop recording? If I just press stop recording. Thank you, Adrian. Thank you, thank you. Thank you for coming, I appreciate it. I'll be stopping by. Oh, actually, I'm gonna email you guys and want to come by soon because I think I have something interesting to share. I'm really curious to hear your guys' thoughts. But so you asked me something.
Yeah.
I'll be here for a bit. I'm interviewing different places right now, and so probably at least for several months. Thanks, Adrian. Take care. Thanks for coming. Manat, if I just click. So don't press stop recording.